I hope everyone's doing well for this particular video. I am Mr. Ish. Thank you for joining me. It's at a request of a particular viewer. Why does this limit particularly equal e? Or why does it approach e in terms of its output? Limit as x approaches infinity, 1 plus 1 over x to the power of x. It was originally coming from a expression which was this, 1 plus x to the power of x divided by x to the power of x, which by means of laws of exponents could be written as this. Under a unifying exponent, and this part right here could be rewritten as 1 plus 1 over x, and then obviously you have the exponent x. If you do the fraction algebra, you have x plus 1 over x, which is equal to that, which is equal to exactly what you see. So this right here and this right here and this right here are equivalent to what you see right over here, and limit as x approaches infinity, it equals e. Why does it equal e? If you were to graph it out and just focusing only on values of x as they approach 0 from the right, because if you put 0 over here, you know you're going to get 1 over 0. We don't like to see that. But if you approach 0 from the right, what happens is what you see over here, a 0 comma 1 y-intercept develops, and then your graph goes in this direction, and what happens is you're looking at a horizontal asymptote y equals e. What's going on is that this function, when you're looking at it from domain 0 up to infinity, notice how I'm putting a circular parentheses because it's not technically in the domain, but it's up to but not including. If you look at this domain, you're looking at a function curve which looks like this, and it approaches a horizontal asymptote y equals e, and it does so. But we don't have to worry about this x approaching 0 anymore, because our limit here is limit as x approaches infinity. If you start taking test values, large x values, test values, example, you can take a value right over here, 9,999. You put them in places of x. 1 plus 1 over 9,999 to the power of 9,999. Look what will happen. You'll get a value close to the Euler's number. I'll do 1 divided by 9,999 plus 1 exponent that same 9,999. I'm getting 2.718. You can imagine as I start making this value larger and larger, closer to infinity, we will actually approach the value of Euler's number, 2.718, 281828, and onwards. It's an irrational constant. You know this, that Euler's number, and that's what's happening. Your function is approaching a horizontal asymptote y equals e, and that exactly is why your end result is this. There's the other portion of this graph. If you look on the other side, it looks something like this. I'm not worrying too much about the exact specifics, but we're only focusing on this side, and that's why I was doing, if I do limit as x approaches 0 from the right for this particular function, which I'm just labeling as f, you are approaching here a value 1. Why are you approaching this value? Because you're looking here at this y-intercept 0 comma 1. But you can't be at 0, because then you have 1 over 0. We don't like that. But you can approach 0, and look what will happen, and I'll show you here on the calculator. If I take a value close to 0 from the right, how about positive 0.0001? And I put that right here in this equation function. Look what will happen. I'll do 1 divided by 0.001, and I'll add that to the 1, which is this one, and then I'll do exponent 0.0001. Look what I'm getting, 1.00. Eventually you'll get closer and closer to the value of 1, which is why you're seeing that. But this right here is exactly why you are approaching e, because your function is approaching a horizontal asymptote. Y equals e is the equation of that horizontal asymptote. Now before I end this video, let me show you one more thing, because I think it's important for you to know it. This right here is a limit which gives you a value of e. Euler's number is the output, but also don't forget there's another limit. Limit as x approaches 0, we have 1 plus x to the power of 1 over x. This also gives you a value of e. And how can you test it out? You can take a value from the right side, hand side, we'll call it positive 0.001. You can take a value from the left hand side, minus 0.001, and put them here in places of this x. And I'll show you here on the calculator what happens, then I'll show you graphically. Let's test this out. 0.001. I'm looking here at the exponent 1 divided by 0.001, and I'll save it. Then I'll do 1 plus 0.001, and I'll do exponent to that save value, and I'm getting 2.7169. That's what I'm getting here, and I'll put it down for you, 2.71692. Let's see what happens from the left hand side, minus 0.001. We'll do the exponent first. 1 divided by 0.001. I'm doing this exponent part, and I'm saving it. Now let's do this part right here, 1 plus 0.001 negative to the power of that, and look what I get, 2.7196. What you are going to see is, as you start making these values closer and closer to 0, you start looking at more and more zeros in here, whether they're positive or minus, this value will become closer and closer to the value of e. That's what will happen. And graphically, what are we seeing over here? We're seeing a function which looks something like this. This intercept over here is 0 comma e. As you approach values of x from the right and from the left at 0, your function approaches this intercept, and that intercept value is e. Hence, you see this for this specific case. So there are two cases, case A and case B. Remember these two different limits, the output, the Euler's number. So you can keep this in the back of your head. And that's it. Thank you. Have a good day.